Hello and welcome to our next lecture. Our exploration of partial differential equations, and today we're talking about yet another type of partial differential equations, namely the Laplace equation. The Laplace equation is a special case of heat transfer and a wave-like phenomenon when the state of the system does not depend on time. Take a look at the heat equation and the wave equation in several dimensions. In 2 dimensions, the heat equation looks like this. Or 2-dimensional wave equation if there is no time dependence in our solution, in other words, we have a completely steady state of the system, t and utt zero out. In other words, if the system doesn't change with time, we just have an equation uxx and uyy equals 0. So the Laplace equation describes both steady-state heat transfer or a steady position of a flexible membrane. Since we don't have any time dependence, there will be no initial conditions. There will only be boundary conditions. But the boundary conditions have to be prescribed for both x and y. In general, if you think about a flexible membrane, that membrane can have any shape. But for the purpose of simplicity and clarity, we're only going to consider rectangular domains, which mean that x belongs to the interval 0 to a, and y belongs to the interval 0 to b. And the boundary conditions prescribed on those boundaries can be either a function u is something, or its derivative is something. But here we have to be careful. If we have a rectangular domain, when we prescribe the function at each one of the boundaries, it's not just a constant value, it has to be a function of x or y. So here, for example, when we prescribe boundary conditions, say we take x equals a, then it has to be a function of y. Here for this boundary, when x equals 0, again the function can have different values throughout this boundary. On the upper and lower boundaries, y is being kept at b or at 0. So it's the function of x. The Laplace equation supplied with boundary conditions that prescribe the function on the boundary is called a Dirichlet problem. Another type of boundary conditions is when a derivative is prescribed. But here we have to be careful about which partial derivative is prescribed at which end. So here the partial derivative has to be prescribed as you traverse the boundary in the orthogonal direction. So for the upper boundary, we have to consider the partial derivative with respect to y. And the lower boundary, we're still talking about the partial derivative with respect to y, but it's a negative function, so we have boundary prescribed as a negative function. At the other ends, we're also going to keep it as f of y and g of y. At the other boundaries, we're going to keep it as f of 1. At the other boundaries, we're going to keep the notation also being f1 of y and f2 of y. But here, we're prescribing the partial derivative with respect to x. And here, again, we're prescribing partial derivative with respect to x because the arrow points in the x direction. In the more general shapes, these partial derivatives are replaced with directional derivatives. When the Laplace equation is supplied with this partial derivative type of boundary conditions, it's called a Neumann problem. We're not going to look at the Neumann problem at all in this class, so we're going to concentrate on the Dirichlet problem. But in order to solve the Dirichlet problem, we have to look at 4 special cases. Now let's consider one such special case. Let's consider a case when the boundary within the domain we have Laplacian of u equals 0. Remember, the Laplacian is the summation of the second order partial derivatives. And almost all of the boundaries are 0. So here, u at x equals 0 of y should be 0. Here, u at x equals a of y should be 0. On this boundary, u at y equals 0 should be 0. And here, u at y equals b should be g2 of x. Since at each end here the other boundary conditions are equal 0, we require that g2 of 0 should be equal to g2 of a should be 0. This is sort of a compatibility condition, meaning that we don't have any tears in our membrane. So if we try to imagine this membrane in 3 dimensions, this is what we have. We have the membrane being kept stationary at almost all of the ends, and then we prescribe some sort of a non-zero boundary. And you would expect the membrane to have this kind of a behavior. Think about an elastic membrane that we keep in this kind of a shape. That looks like a plausible shape that this membrane would assume. Let's assume that u of xy is a summation of building block functions, each depending of x and y, and un of xy being the product of x times y of y. And then u sub n satisfying the Laplace equation meaning that u sub n xx plus u sub n y should be 0. We assume that each one of those u sub n satisfy the boundary conditions where the boundary is 0. So u sub n at x equals 0 is 0. U sub n at x equals a is 0. U sub n at y equals 0 is 0. And u sub n at y equals b is something we're not going to specify. Plugging x times y into the differential equation, we get that x double prime times y plus x times y double prime should be 0. This leads to x double prime over x being equal to minus y double prime over y. And therefore, it must be some kind of a constant. Just as before, I'm going to assume that the constant is negative sigma, and then x double prime here has this equation. And y has this equation. Plug in the boundary conditions, we get that x of 0 times y of y should be 0. We also know that x of a times y of y should be 0. We also know that x of x times y at 0 should be 0. And then that's it for the 0 boundary conditions, which leads to the boundary conditions on x being x of 0 being 0 and x of a being 0, and on y we only have the condition y of 0 has to be 0. We already covered the problem with x. The differential equation reads x double prime plus sigma x equals 0. The boundary conditions being 0 at both ends leads to sigma being simply pi n over L. Then the length of the interval here is a, and x of x simply being sine of pi n over a times x. This leads for the following problem for y. We get that y double prime minus pi n over a squared times y should be 0, and y of 0 should be 0. Solving this differential equation gives us that y of y must be some kind of a constant, that's called alpha 1, e to the minus pi n over a y plus alpha 2 times e to the positive pi n over a times y. To satisfy the condition that y of 0 equals 0, we get that alpha 1 plus alpha 2 should be 0. Therefore, the constants are just negatives of each other. So we can say that alpha 2 equals negative alpha 1, or just alpha, and therefore y of y can be written as alpha times e to the pi n over a y minus e to the minus pi n y over a. Just as before, without loss of generality, since everything will be multiplied by Cn afterwards, we can assume that alpha is just 1. And therefore, the final form for y of y is just e to the pi n over a y minus e to the minus pi n over a y. And the building block solution u sub n of xy simply is e to the pi n y over a minus e to the minus pi n y over a times sine of pi n x over a. And therefore the full solution is just a summation, and we'll have to go from 1 to infinity. The summation Cn e to the pi n over a y minus e to the minus pi n over a y times sine of pi n x over a. So the final step here is to figure out how to translate the function g2 of x at the other end into coefficients Cn. We're given that u at y equals b is g2 of x. Therefore, since u of x is a summation, it is a summation as n goes from 1 to infinity, Cn times the difference of the two exponentials, e to the pi n This time y equals b, so it's pi n b over a minus e to the minus pi n b over a multiplied by the sine of pi n x over a. So we see it's almost the sine series for the function g2 of x. But there is this coefficient in front. So Cn must be 2 over L, which is, in this case, the length of the interval is a, so it's 2 over a times 1 over e to the pi n b over a minus e to the minus pi n b over a times an integral from 0 to a of g2 of x times sine of pi n x over a dx. So this is only one type of problems when we have only one boundary non-zero. We can do the same for every other boundary, meaning that we can assume that 3 boundaries are 0 and then 1 boundary is non-zero, and derive this series expansion for each boundary case. And then if we have 2 or 3 or 4 boundaries non-zero, then we can separate them into these 4 subcases and then add up the series expansion for each subcase. We can add them up because every subcase only has a non-zero boundary in one place, and all 3 other boundaries are 0, adding nothing to the other subcases when we add them up. The only problem there is that we will have all of the corner points of my rectangle being 0, because that's the compatibility requirement for all of those boundaries, that the boundaries go to 0 at all of those other ends. This is really not a complicated problem to solve. We're going to see in the next lecture how we're going to solve a problem where the boundary is non-zero even at the corners. For now, let's consider a simple problem when I have x going from 0 to 2, y going from 0 to 4. The boundaries are 0 except at the boundary at y equals 4, which is a non-zero parabola. So the solution here will be a summation c sub n times e to the pi n y over a, so pi n y over 2, minus e to the minus pi n y over 2 times sine of pi n x over 2, where each sub n is computed as 2 over L, so it's going to be 2, the length for x is 2, so it's 2 over 2 times 1 over e to the b is 4, so it's going to be pi n b is 4 over a, which is 2, minus e to the minus pi n 4 over 2 times an integral from 0 to 2 of the function g2 of x, which is x times 2 minus x, times sine of pi n x over 2 dx. Adding up all those functions will give us the solution. Let's switch to Mathematica and see what happens. So here I have a setup. ck are computed as 2 over L, 2 over a is 2, times 1 over the exponentials, times the sine series decomposition of g2. Then I will add up all of those solutions, multiply by their respective coefficients, create a function u, and plot it from 0 to a in terms of x and from 0 to b in terms of y. And I also outline the boundary here just so that we can easily see it. So let me evaluate everything. We define a, b, f1, f2, g1, and g2. Let's plot it. It's just a downwards parabola. Let's compute the coefficients. Coefficients are computed. Let's go ahead and plot it. So this is what a steady state heat transfer or a steady state elastic membrane is going to look like if we prescribe this on the boundary this way. In the context of a heat equation, If we assume that this is the heat profile of something that the membrane is touching, then the temperature is going to be very high, and then since the temperature at the other ends is kept to 0, the heat will just flow this way, and that will be the temperature profile of this membrane. If we consider this an elastic membrane being deformed, so the membrane is clamped at 3 of its boundaries, and then at this boundary this profile is maintained, so the boundary is under load, this will be all other positions that this membrane takes. So if you can assume this being sort of a, if I flip it around, if you consider this being a roof of a building, where at one end there's a very high load, then this is the deformation of the roof that we're going to see. This is not entirely physically accurate. I want to add a little bit that if we're talking about the materials that resist bending, which is what our string is not resisting, or our membrane, a flexible membrane, is not resisting bending from perspective of this differential equation. If we have an elastic membrane that resists bending, then the differential equation will have to include fourth order derivatives. So it's a little bit more complicated than that. So, but if we assume a thin membrane, like a plastic membrane that is stretched and then put under load, then this will be the profile of this membrane. So if the membrane is easy to bend, no internal torque kind of stresses within itself, then this equation will describe the behavior of such membrane. All right, this is it for this lecture. In the next lecture, we're going to consider more general situations when several boundaries are non-zero, and in addition, the corner points may also be at non-zero locations. And we're going to develop a 5-step method of attacking these kind of problems. All right, thank you for listening. I hope you enjoyed today's lecture, and I'll see you in our next video.